This paper describes complexity theory of neural networks, defined by tensor decompositions, with a review of simplification of the tensor decomposition for simpler neural network architectures. The concept of Z-completeness for a network N is defined in the existence of a tensor decomposition for that particular N. Welcome to a talk on complexity of neural networks, by Dr. Bheemaiah Anil, narrated by Amazon Alexa, in architectures for supervised and unsupervised learning, with complexity definitions with a Rademacher complexity defined for both cognitive learning and machine learning models using continuous computatable functions. This talk introduces the concept of Z-completeness, with an existence theorem and an incompleteness theorem. Z-completeness is defined as tensor compatibility, with Gödel's provability in the existence of solutions, practicable in the context of model theory and approximation theories observed in NP-complete problems. The proofs are published elsewhere and beyond the scope of this talk. Incompleteness with prime numbering, similar to Gödel's incompleteness of provability, is defined. Several examples of architectures, similar to the ResNet convolutional architecture and in generative AI, are presented to illustrate CP, Tucker, and other methods of tensor decomposition, to improve the efficiency, in resource and time, for less intensive implementations. Two theorems are presented, to investigate the realm of Z-completeness in learning, both supervised and unsupervised, and in the realm of data mining architectures. Complexity theory applied to learning helps with evaluating the A/B testing required for the supervised learning, and to evaluate in metrics the fitting of the ensuing models. The learning is then learned to practical real-world scenarios. The incompleteness theorem proves the incompleteness of a closed-form tensor description of networks in the framework of Gödel's incompleteness of provability, and explores the limitations of symbolic reduction and decomposition of tensor expressions for a simplification of a network architecture for less intensive computation. Tensor decomposition can be achieved with several approaches, the Tucker and CP being the most common. Other approaches to matrix representations of tensors and singular value decompositions are also practiced. We talk about two tools, one built into Wolfram and the other built into the Python language, called TensorLi. In the next few slides we illustrate CP and Tucker reduction of tensor rank using a few examples in CNN and generative AI. Tensorization of neural network architectures leads to TensorFlow representations, imported to Wolfram's neural network repository. NetChain is a Wolfram command that lets you design a chained network architecture, which can be represented visually as a graph with NetGraph. The same architecture is directly amenable to representation as a tensor representation, which can be compressed to canonical forms, which simplify CNN computations. In the case of ImageNet and ResNet 50, used in Mapillary, an R14 paper by Su, Lee and Bhattacharjee, proves compression of ResNet's convolutional layers is possible by both CP and Tucker compressions. The Rademacher complexity measure in the range -1 to 1, using continuous computable function, is used to determine the complexity of the tensor neural network, for both supervised and unsupervised learning. For an A/B testing inspired model, a partition of the A and B sets is determined by the complexity metric, to prevent overfitting and measure the applicability of the model to transfer learning. The VC dimension can also be determined using simple mathematics found in several references, including Lu 2015. The VC dimension is used to design the training set for the network. We illustrate complexity dimensionality with the attention gone in ResNet 50. Three techniques for compression of tensors are described with two examples, a ResNet 50 network and attention gone network. In the next 10 slides I describe results from two papers, by Su and others, 2018 from R14, and by Ma and others, 2021. The first paper describes the use of CP compression, Tucker compression, and tensor track compression. The second paper describes the use of CP compression alone to compress the generator convolutional networks tensorially. From the paper by Su, 2018, are the following definitions of tensor decompositions. CP, Tucker, and tensor track are described, followed by slides on the compression algorithms. CP compression is described in this slide. To quote the slide, CP decomposition is a direct generalization of singular value decomposition, SVD, which decomposes a tensor into additions of rank I tensors, outer product of multiple vectors. Specifically, given an M order tensor E subscripted X to Gene 1, CP decomposition factorizes it into M-factor matrices as shown in the slide, where R is called the canonical rank of the CP decomposition, which is allowed to be larger than the I's, where I belonging to a tensor space of reals with a real covariate, is an all-ones vector of length R. The takeaway from this slide is that CP compression reduces the tensor T to a set of M smaller tensors represented by I, which lead to a lower number of floating point operations for a combination of smaller tensors and a smaller number of independent parameters in the network architecture to 2. In the supervised learning. In this slide we describe the Tucker compression algorithm. To quote from the slide, Tucker decomposition provides more general factorization than CP decomposition. Given an M-order tensor T, Tucker decomposition factors it into M-factor matrices, and an additional R n-order core tensor C. Notice that when R subscript 0 is equal to R subscript M is equal to R and C is a superdiagonal tensor with all superdiagonal entries to be ones, aka identity tensor, Tucker decomposition reduces to CP decomposition, and therefore CP decomposition is a special case of Tucker decomposition. With Tucker decomposition, a tensor is approximately by M terms in R, thus Tucker decomposition is a superset of CP compression, with dimensionality reduction and a reduction comparable with the CP algorithm in reducing computational load in floating point operations and parameters. Tensor train is yet another compression algorithm described. To quote the slide, tensor train decomposition factorizes a M-order tensor into M interconnected low-order tensors where the R's are known as tensor train ranks, which controls the trade-off between complexity and accuracy of the representation. With tensor train decomposition, a tensor is represented by M entries of lower-ranked tensors. The predominant computing layers compressed include the convolutional layer and the dense layer. If one studies the graphical representation of the ResNet50 using the Wolfram netgraph command, one can observe that these two layers are computationally most intensive, and profiling shows that most of the floating point operations are in these two layers. In the paper by Su and others, compression is applied to these two layers. In brevity of time limitations, only the compression of the convolutional layer by the CP, Tucker and tensor train methods are described. The tensor expression for the convolution layer is described in equation 35. Equation 36 describes the decomposition to lower-ranked tensors, and equation 37 describes the learning aspects of backpropagation in the net chain. In this slide, the convolutional layer with the kernel K is decomposed to 3 Tucker components, and equation 39 describes the 3 ensuing layers of computation in a Tucker approximation to the original kernel. Equation 40 is the backpropagation for the convolutional layer. Tucker leads to a M tensor representation, similar to the CP approximation, proven to be successful in a 15 to 20% reduction in floating point operations as published in the cited reference. In this slide, tensor train decomposition is used to split the kernel to several lower-ranked components, as described in the previous slide. Equation 42 describes the compressed kernel tensorization, and equation 43 describes the backpropagation expressions. If we recall, tensor track leads to rank reduction as an approximation, similar to CP and Tucker approximations. This slide describes a successful experiment with 15 to 20 reduction in computational load and in a decrease in parameters, as described in the cited reference. In this slide we describe results from Ma and others in their 2021 paper, publishing successful results in runtime efficiencies in the use of CP-based compression in the generator layer. The above slide indicates a schematic of the GON architecture, with the generator layer indicated. The next 2 slides indicate the splitting of this layer into 3 sublayers and the compression algorithms and work. Equation 4 reproduced from the publication is the tensorized expression for the network, and equations 5, 6, 7 indicate the 3 layers corresponding to the CP compression, which are proven in the publication, to lead to statistically significant improvements in network performance by up to 30% without any loss in the quality of the generated images. The above schematic indicates the CP decomposition of the generator layer as 3 layers called pre-trained layers, using a series of autoencoder layers. The autoencoder layers are used in the pre-training as the generator layer is unstable in CP decomposition and needs to be pre-trained for feasibility, using the autoencoder layer as described in the cited reference. 2 references used in this review of compression techniques are presented. The last part of this talk has an addendum on 3 examples of neural networks and graphical dumps, which may be used as a reference. The final slide is a slide on future work. The final part of the talk is the addendum with 3 examples: the cyclic GAN, the attention GAN, and the ResNet 50 used to explain and review tensor compression techniques. While the reviewed information is based on work at CMU and is based on TensorLi and Python and paper and pen calculations, future work would use the tensor manipulation functions of Wolfram and several GISTs to be made available for theoretical tensor definitions of network architectures and compression techniques. This slide presents a graphical diagram of TE-ResNet architecture, from the netgraph command or from CoRUG 2019. A net chain dump of the ResNet 50. This slide represents a graphical representation of the attention GAN architecture from R14. The architecture of cycle GAN is presented from R14. A net chain dump of the cycle GAN tensor layers. The net chain and net graph commands as well as the commands for tensor reduction and canonicalizing are presented as future work. A need to add tensor decomposition as symbolic refactoring into the Wolfram language as future work. Future works involves creation of GISTs of Mathematica code for symbolic refactoring for CP, Tucker and TensorTrain, amongst other decomposition methods for compressing network architectures. Applications involve use on wearables, use in medical use cases, and the use with TensorFlow Lite with the Mathematica APIs. With this we conclude the presentation, leading the floor to the question and answer session. Thank you for listening to this talk. This talk will soon be made available on Amazon Alexa, as an interactive skill.